Hello everyone. So this will be my first video ever, and it's also the first video in the series on quantum mechanics following Sakurai's classic textbook. So I will be going through the textbook in order, trying to explain the topics and providing any additional insight that I have. I will be starting now with chapter 1 and giving an introduction on the Stern-Gerlach experiment. So this experiment was carried out in 1922, and the reason it's very popular in a lot of quantum mechanics textbooks is because it shows some of the peculiar behaviors that need quantum mechanics in order to be explained. So they cannot be explained through our classical theories. And this experiment is one of the most quantum mechanical systems out there. So here's the general explanation of the experiment. So if you have an oven over here, and it is heating a lot of silver atoms. And then in the oven, you have a hole which allows the silver atoms to exit. And then the silver atoms actually go through an inhomogeneous magnetic field, which points in the Z direction. It could have pointed in any other direction. It doesn't matter. We just had to pick a direction. So we just say the Z direction. So the question is, what pattern would we actually see? So let's start by talking about what we actually know about this system. So silver has 47 electrons, which means that 46 of them are paired into pairs of spin up, spin down, and there's one electron that's unpaired. Therefore, the atom has a total angular momentum, which comes from the intrinsic spin of that one unpaired electron. So we can say that the magnetic moment of the atom should be proportional to the spin of that unpaired electron. So we can see that relationship over here. Now, the force that is experienced by the atom is given by this equation over here, where force will be equal to the gradient of the magnetic moment dot the magnetic field. We will choose to focus on the Z component of the force and the Z component of the magnetic moment, since we chose also to orient our magnetic field in the Z direction. Therefore, the Z component of the force ends up being the Z component of the magnetic moment times the partial derivative of the magnetic field with respect to Z. If we have, so the important part about this equation is that we can see that the force is directly related to the Z component of the magnetic moment. If the Z component of the magnetic moment is positive, we have an upward force. If it is negative, then we have a downward force. Also, we can see that it's directly proportional to it. So the bigger mu Z is, the bigger Fz, and the same thing, the smaller mu Z is, the smaller Fz. So we can therefore say that the beam is expected to split according to the value of mu Z. So here's our classical prediction. So the atoms that are coming from the oven, they don't have any specific preferred orientation. They have random orientations. So therefore, their magnetic moment can point in any direction. And so their Z component of the magnetic moment can have values which range from plus mu to minus mu. So plus mu represents an atom whose magnetic moment points in the Z direction. Minus mu represents an atom whose magnetic moment points in the negative Z direction. And anything in between represent an atom whose magnetic moment points in any other direction, which is a combination of X, Y, and Z directions. So what we classically expect is that the silver atoms will be, the silver atom beam will be split according to the mu Z values, and it will produce this continuous patch which would correspond to the continuous values of mu Z. So for example, over here, we have the point which would represent mu Z equal to mu. Here we have mu Z equals to minus mu. And another example here, we have when mu Z is equal to 0. So this is what we expect classically. So we haven't said or done anything wrong. We're just talking about what we would predict based on what we know about the theory. However, these are not the actual experimental result that we see. What we actually observe is a quantum mechanical behavior So the beam ends up being split into two distinct regions, one representing mu z equals to mu, and one representing mu z is equal to minus mu. So we say that the beam is split into two distinct components, which we called up and down spin. So this is one of the first evidence for the peculiarity of quantum mechanic behavior. So now I will be talking about sequential Stern-Gerlach experiments, which simply means that we pass the beam through multiple Stern-Gerlach devices of any orientation that we want. So I'll be representing the Stern-Gerlach devices just using a rectangle like this, because we don't no longer care what the device is actually made up of or what it looks like. The only thing we care about is the direction of the magnetic field, which I represent over here with a letter. So this represents the magnetic field in the z direction, x direction, y direction. So this is our first setup that we're going to be considering. So this is our beam coming from the oven. It goes through a SGZ device, and we already know the output of this. So this is going to split the beam into two components: spin up, which we denote by SZ plus, and spin down, which we denote by SZ minus. So if we block the spin down component, and then we only let the spin up component, SZ1, continue to pass through another SGZ device, we see that the output of that device only produces an SZ plus beam, and the SZ minus beam is actually missing. So the results of this experiment are pretty intuitive. We blocked the spin down component after the first Stern-Gerlach device, which means that only the spin-up beam was entering the second Stern-Gerlach device, so it makes sense that the final outcome is missing the SZ minus beam. So there's nothing weird going on over here. This is a result that we could have predicted naturally. So this is the second setup that we're going to be considering. Similar, same as before, oven, beam coming out of the oven. It goes through an SGZ device. We see the SZ plus and SZ minus. We block the spin down component and let the spin up continue. But now we pass it through a Stern-Gerlach device with a magnetic field in the x direction. And the outcome of this experiment, we see a spin up x component beam, SX plus, and a spin down x component beam, SX minus. And these two beams have the same intensity. So the intuitive part about this part of the experiment is that we actually got two beams as our output. This makes sense because previously over here, we only filtered for the Z component of the spin. So there's no reason why we would assume that filtering for the Z component should eliminate one of the X components of the spin, so SX plus or SX minus. However, the two beams having exactly equal intensity is actually the intriguing part. Why is it that when we passed a spin-up Z component beam through an SGX filter, we got equal amounts of SX plus and SX minus? So there's something weird going on. So what you could, something that you could hypothesize is that this SZ plus beam is made up of exactly half of SX plus component and the other half has SX minus component. So this is not like, this is a reasonable assumption for you to make. You can, you have to do more experiments to actually verify if the assumption actually makes sense. However, let me just explain why this assumption would be problematic even without looking any further at this. So there's nothing special about us choosing the X direction over here. So we could have chosen the Y direction, we could have chosen any other direction pointing anyway. And we would expect our results to be the same. The output from the second SG device should have two beams of equal intensity representing spin up of that orientation and spin down of that orientation. So does that mean that SZ plus over here has equal amounts of spin up and spin down of any orientation that we choose? So that's not very logical. Like, where would that information be coming from? How would the atoms that are coming from the oven, which are being heated up and they have random orientations, why would they be organized in that way? So now we will consider a third setup, which will hopefully clarify the setup a little bit more and try to explain what is actually going on after that. So our third setup over here is similar to the previous one. The beam coming from the oven, it passes through an SGZ device, and then we have the spin up Z component, spin down Z component, filter it by blocking the spin down component, and then pass it through an X-oriented SG device. So the output of that device, we already know from the previous setup, is that we're going to get equal intensity SX plus and SX minus. So let's filter this by blocking the spin down X component and letting the spin up X component continue and go through another Stern-Gerlach device that's in the Z direction. So the really surprising part is that the output of this actually gives us SZ plus beam and SZ minus beam with equal intensity. So this is really weird because over here we had filtered by excluding all the SZ minus beam. And then what we did over here is simply measure the X component of the spin, and then we split it based on that. So we have a spin up X beam and a spin down X beam. So how come when we are passing it a second time through an SGZ device, we get this SZ minus beam again? Where is this information? How is this SZ minus a product of this beam over here when we actually blocked it before passing through the SGX device? So this result is very weird. This is basically the essence of quantum mechanics. So measuring the X component of spin erased all the information that we knew about the Z component of spin. So this sounds weird right now, but we'll explore this more in details after. So what we're gonna do next is try to study this further with an analogy with light polarization and try to see where else in physics can we get similar results. So like I said, we will study the behavior of polarized light to try to understand a bit more the results that we got from the sequential Stern-Gerlach experiments. So let me just explain one thing that will be very important, what a linear polarizer is. So a linear polarizer is a device that filters light by only letting the light beams that are parallel to the polarizer's direction pass, and it blocks all the other components of the light. And then the outgoing light from the polarizer will have the same orientation as the polarizer itself. So for example, an X polarizer will only let in the light that is along the X-axis, and it will block all the other components of the light. Similarly for the Y polarizer. We will also define them over here, conventions for X prime and Y prime polarizers. So X prime polarizer is a polarizer whose axis is at 45 degrees to the X-axis, and Y prime polarizer is a polarizer whose axis is at 45 degrees to the Y-axis. So we will consider some setups, and we will try to, after that, we will try to compare them to our Stern-Gerlach scenarios. So consider the first setup where we have a beam of unpolarized light. So unpolarized light means that it has equal amount of X polarized and Y polarized light. So if we pass it through an X polarizer, it means that only the component of the light that is parallel to the X-axis will pass through, and it will block all the other components of the light. So the outcome of this should be X polarized light, which is a beam of light that only has an X component. So if we pass this X polarized light through a Y polarizer, we will see no output, so no beam will come out, because this beam over here that's entering the Y polarizer does not actually have any component along the Y axis. So this polarizer will not let any of it pass. So that's the first setup that we're going to be considering. The second one, again, we have a beam of unpolarized light. We pass it through an X polarizer. And then, like I said earlier, only the X component of the light will pass, so we will have X polarized light. However, now, we pass it through a second polarizer that is an X prime polarizer. So this X prime polarizer will not block all of the X polarized light, because you can easily see that X polarized light does have some component that is along the X prime direction. So some light will pass, which will now have an orientation in the X prime direction, and then we will pass this light through a Y polarizer. So, contrarily to our previous setup, this Y polarizer will no longer block all the light, because as you can easily see, a light that is in the X prime orientation does have some component that is along the Y direction. So this polarizer will have to let some light in, and therefore we will see a beam. So let's see how would this actually relate to our Stern-Gerlach experiments. So let's make the certain correspondence. So let's identify the SZ plus atoms with X polarized light, the SZ minus atoms with Y polarized light, the SX plus atoms with X prime polarized light, and the SX minus atoms with Y polarized light. So let's see how this actually translates, how this translates the polarized light experiment to our actual Stern-Gerlach. So this beam over here, which was unpolarized light, which means that it has equal amounts of X polarized light and Y polarized light, represents the beam that is exiting our first Stern-Gerlach device that's pointing in the Z direction. So this would represent an atom beam that has SZ plus and SZ minus. And then what we did in our experiment is that we blocked the spin down component, and this is basically what the X polarizer is doing. It's blocking one of the components of the unpolarized light, and it's letting the other half pass. So the X polarized light here would represent our SZ plus beam, and we're letting it pass through another SGZ filter. And the outcome that we saw in our experiment is that we will see an SZ plus beam, but the SZ minus beam was missing. So this is similarly here, the Y polarized light, which would be choosing only the white polarizer, which we would be choosing only white polarized light, would produce no output. And this makes sense with our correspondence, since Y polarized light is in correspondence with the SZ minus beam, and which was missing from our experiment as well. So we can do the similar type of analogy with the second setup that we have over here. I won't do it in details, but you can do the correspondence. It's very helpful to actually understand the problem. So this setup over here is analogous to the setup where we pass the beams through an SGZ Stern-Gerlach. We filtered it, then we passed it through an SGX Stern-Gerlach SGZ device, and then we only let the SX plus pass, and then we passed it through another SGZ device. And at the end, surprisingly, we got two beams, SZ plus and SZ minus, with equal intensities. So this was just to see, so what we're trying to do right now is just to try to understand, trying to bring our problem to something that we're more familiar with, which is light and waves. So let's see how we can give a mathematical description to the light polarization problem. So a linearly polarized light, which is moving in the Z direction and is polarized in the X direction, has an electric field which oscillates in the Z direction. And it's expressed through this formula over here. So this is an electric field that has a magnitude of E naught. And this is an oscillating function which oscillates in the X direction. And then we can say the same thing about a wave that is polarized in the Y direction and any other direction. So we can say the same thing about the X prime direction and the Y prime directions. So if we take our electric field, which is oscillating in the X prime direction, so it's X prime polarized light, and let's actually draw this over here. We can see that x prime can actually be written as a linear combination of x and y, right? So x prime would just be equal to cos of 45 degrees times x plus cos of 45 degrees times y, which gives us 1 over square root of 2 x plus y. And similarly for y prime, it gives us minus cos of 45 degrees times x plus cos of 45 degrees times y, which gives us 1 over square root of 2 minus x plus y. So therefore, we can define a polarized beam by making the substitution of what we defined x prime and y prime to be over here in terms of x and y. And therefore, we can see that x prime polarized light and y prime polarized light beams are linear combinations of x polarized and y polarized. So if we go back to our initial correspondence where we identified SZ plus and SZ minus with x polarized light and y polarized light, and we identified SX plus and SX minus with x prime polarized light and y prime polarized light. So if we apply this correspondence and we use the notation where we represent an SZ plus or minus state using this notation over here, this is called a Dirac ket, and similarly for SX plus or minus. So we will see this notation in detail when we go to the mathematical treatment of quantum mechanics. So if we do this correspondence, we can deduce this formula over here where we have written SX plus and SX minus as linear combinations of Z plus and SZ minus over here. So this now is just an assumption. We can't take this to be a fact, but we will derive this expression explicitly later on. So I hope this helped you a little bit try to understand why is it that when we actually pass an SX plus beam into an SZ filter, an SZ Stern Gerlach device, we actually do see some SZ plus and some SZ minus beam. So the next thing we're going to talk about is how would we actually represent SY plus or minus. So a very important thing to note is that for the sequential Stern Gerlach experiments that we considered, that they should behave exactly the same way if we replace every x with a y. So we have our experiment over here, and all we did was replace the SGX device with an SGY device. And here we have a spin up Y component and a spin down Y component. And then we carry out about the same experiment and we should get the same output of SZ plus and SZ minus with equal intensities. So what we know from our previous discussion on SX plus and SX minus is that we would like to have SY plus or minus as linear combinations, linear superposition of SZ plus and minus states. So also what we want is that our SY plus or minus states not to be mathematically identical to our SX plus or minus states. We want them to be distinguishable so that if we're working with both X and Y, we were able to make the distinction between them. So in order to do this, we resort to light again, and this time we used circularly polarized light. So circularly polarized light looks something like this. So this is moving along the Z direction, and we can already see that circularly polarized light should be expressible in terms of a linear combination of X polarized light and Y polarized light. The difference between this and between the X prime polarized and Y prime polarized light that we considered previously is that for circularly polarized light, its X and Y components are 90 degrees or pi over 2 radians out of phase. So we can either have the right or left circularly polarized light, and we define them based on whether the X or Y component are lagging or ahead in phase. So there's no specific convention as to which one should be lagging and which one should be ahead. So we will use the convention where right circularly polarized light has an electric field given by this formula over here. And as you can see over here that its Y component is pi over 2 ahead in phase, and left circularly polarized light is given by this formula over here, and the phase of the Y direction is pi over 2 lagging in phase. So in order to actually represent this, we will move on to using complex notation. We define a new electric field over here, denoted by this symbol, epsilon, and such that our fields that we defined previously are actually the real component of epsilon. So I'll just give a little side note here in case some of you might struggle with this. So we have Euler's formula, which links e to the ix to cos x plus I sine x. The real part of e to the ix is cos x, and the imaginary part of e to the ix is sine x. So therefore, if we compare this with our formulas over here, we can say that, for example, cos of xz minus omega t is just the real component of e to the I kz minus omega t. So we can work in this notation to simplify the math, and then if we want to go back to our initial notation, all we have to do is just take the real part of our final expressions. So we write the complex field right now just by making the substitutions according to these definitions. So we get 1 over square root of 2 e to the I kz minus omega t in the x direction, plus 1 over square root of 2 e to the I kz minus omega t plus or minus pi over 2 in the y direction. So the reason there's a plus or minus here, it's because I'm representing both right polarized light, represented by the plus sign, and left polarized light, which is represented by the negative sign. So this over here, this exponent, we can easily split according to the exponent properties. And then we can use the fact that e to the plus or minus I pi over 2 is equal to plus or minus I, where I have again just used Euler's formula. So this gives us that the right and left polarized lights are represented are represented by 1 over square root of 2 e to the I kz minus omega t in the x direction, plus or minus I over square root of 2 e to the I kz minus omega t in the y direction. So we will start by making a correspondence similar to what we did in the previous part with the sx plus or minus. So we make the correspondence that sy plus atom is corresponding with the right circularly polarized light. Sy minus atom, it corresponds with the left circularly polarized light, and sz plus and sz minus are again in correspondence with x polarized light and y polarized light. So if we write this over here according to our correspondence, we get that sy plus or minus is equal to this expression over here, which again we have been able to write as a linear combination of sz plus and sz minus. So again, this is a tentative solution that we have used from an analogy of light. We can't take it for a fact, but we will derive it later when we actually study this problem after having derived the mathematical formulation of quantum mechanics. So just one comment over here, we saw how we can represent Sx plus or minus and Sy plus or minus as linear combinations of Sz plus or minus. And we see that the vector space that we need to do this representation is a two-dimensional vector space. However, it has to be complex in order for the Sx representation and Sy representation to be linearly independent. And we can see the complex nature of the vector space by this I over here. So I will stop here for now. Next time we will dive into the mathematical formulation of quantum mechanics. And I hope everything was clear up to now. If there are any questions, please feel free to leave them in the comments. And I'll see you next time.